Hello and welcome. Today I will show you MBUS to wireless MBUS integration manual we have prepared. This approach, this manual is applicable to ACRIOS converter 101 LMD and LMEAC also, but you will most likely want to use it with the battery powered version of our LoRaWAN to MBUS device. If you want to use it, you need to first load to the stock device this Lua script so that it works, but the best is to get in touch with us and make this work together with us. So, typical use case for this Lua script I will show you is that you have an MBUS device, as you can see on the video, and you want to make it available wirelessly. For example, you have your own wireless MBUS infrastructure which you would like to use for readout, or you can use our device ACR-CV101NWD, which is the wireless MBUS to narrowband, which can do the remote readout of wireless MBUS for you. So I will skip benefits of MBUS. You can go into details in the document, which will be in the description of the video. And I will skip directly to the functions. You can configure the encryption key. However, by default, the internal secret key is used for encryption of the payload you read out over MBUS. You can configure the initial delay of the MBUS line. Sometimes some people call it preheat. It is the time for which the MBUS line is turned on before the actual request to the MBUS the slave is executed. By default there is 5 seconds. Some devices require more, sometimes just 2 seconds is okay. However, it is really important to test where is the limit, or to check the datasheet of your meter. It is good to have there a certain margin on one hand. On the other hand, it is good to minimize this time, because it considerably influences the battery lifetime of your device. You can configure the baud rate and other parameters of the MBUS. You can do VIF DIF filtering, which we will use today, and it is very important to minimize the payload, because the payload on wireless MBUS is limited. And you can set a ratio between the period of how often you execute the MBUS readout, the actual readout of the MBUS device, and how often the data which is cached, which is stored in the ACRIOS converter, should be transmitted over radio to the air. Yeah, these two go together. So the out-of-box behavior, you connect the power and the device will read out the MBUS line. In case of the Engelmann sensor star, you should get a payload like this if no filter is set up, and this payload is then encrypted and encapsulated into wireless MBUS and transmitted. The CI field we use is proprietary, because there is no standard way how to encapsulate an MBUS device into wireless MBUS in a way that you can later unpack it and have the information about the secondary address of the MBUS target, because you need to have the address of the converter because of the ciphering, but you also need later to have the information about the address of the end device. So we have done our custom encapsulation. However, it uses I would say standard elements such as AES, and you will see later how it works, and it's quite straightforward to implement. So this is the device you see also in the video, which we will read out today, and I'm getting slowly to the payload parsing. So once you read out the MBUS line, you can also parse it using either this nice parser from Mr. Miller. You can also use JMBUS parser. You can use libmbus and implement the parser on yourself, and you can also leverage our backend where we make some of the parsers available. As I said, you can use both battery powered and AC powered version of our device, and here we did some basic measurements so that you have some estimation on the battery lifetime. So for example, if you read out the MBUS line every 15 minutes, the battery lifetime should be 1.5 years. If you read it out every 60 minutes, it is approximately 5 years, 5.1 years. And these numbers are given, if I'm not wrong, for a single D battery. In our device you can also have a double D cell battery. Yeah, so this would practically double the lifetime. Here we mentioned the initial delay, which changes a lot the battery lifetime. These calculations are done with a 5-second initial delay. There is the limitation in the length of the MBUS frame, which we can encapsulate. It is 126 bytes, and the script is done in a way that it will tell you that the payload is too long, and it will simply refuse to transmit it, because currently we are limited to this number. In future hardware release, we will allow up to 255 bytes to be transmitted, but currently there is a limitation given by the hardware. And of course it is important not to connect two MBUS masters at once to 1 meter. This is generic information, but it is good to repeat it. Okay, so I think it's good time we go directly to the actual script, which I will explain shortly, and I will match it to what I've already mentioned. Here is the link to the script. It is available on our GitLab repository, which is made public. And but maybe it will be better if I will read it out from the device, so that we will have this, but you can of course also click this link. So I will open our ACRIOS IDE. I will click on the connect button, and because I would like to go into the config mode, I directly click on config, and it is trying to connect now. Now I will plug in the battery, and the device is blinking, which means it is in the LoRa bootloader we have there. So I can hold the button, it will skip the bootloader, or I can wait, and it will also get to the application, but because I don't want to waste your time, I will press the button. Okay, we are in the application and we got connected. You can see here the type the type and the firmware revision. So I will click on read, and this will read the Lua script, which is stored inside, which is implementing the application logic. You can of course modify the application logic if you want, but to make the customization easier, and so that you don't need to go and modify this code, you can also do some little customization here. You can define your own key here, which needs to be 16 bytes long. You can modify those parameters which I have already mentioned, and you can modify here how often the transmission should be done. Here we have every 3 minutes, and this 20 multiplied by 6 means that every 3 minutes the transmission is done, and every multiplied by 20 gives you 60, and multiplied by 6 gives you 360, and this is 6 hours, which means that every 6 hours the MBUS will be read out to refresh the data. Yeah, this changes a lot the lifetime, as the transmission on wireless MBUS is quite fast. Even if we transmit every 3 minutes, this doesn't influence much the battery lifetime. And then is the actual implementation. Here is the function to send the payload. You can see that the payload starts with this decryption verification bytes, then there is the payload, but we will get to that later in the description of the payload. Here is the on-wave function. This is what happens when you press the button or when 3 minutes elapse. And this is on startup, and this happens just once. And here we have settings of our VIF DIF filter. Here is an example for the Engelmann sensor star. So without applying the VIF DIF filter, you can see that we can get approximately 185 bytes. If I scroll it like this, you can see it's quite long. And if I apply the VIF DIF filter, saying that I am only interested in this information, in the fabrication number, timestamp, energy, volume counter, power flow, flow temperature, return temperature, and temperature difference, I can set up the VIF DIF filter like this, and the reduced emboss frame only has 69 bytes. Yeah. So this is how it works. Here we put together other parameters of the wireless emboss frame, which is then used for encapsulation. You can see here that we use CI field of A0, which by the standard means that the payload which follows is application specific. We use device type of hex 37, which says that we are radio converter unit, meaning that we are a wireless emboss device which connects some other device to retransmit its data. So we try to keep as close to the standard as it is possible, but the encapsulation of the payload is custom, is application specific. However, we are using AS128, which is a standard way how to do the encryption in CTR mode. Okay, so we quickly check the script. And we check that the script is actually there in our device, which is very important if you want the behavior we expect. So now I will disconnect from the device. I will refresh the tab and connect without clicking to the config, which will only show us the serial prints of the device, only the printout. And now what we can do, we can try to actually receive the data. Here you can see that the script is starting. He gives us here his wireless emboss identification, which is the device address, which should be on the label of the LMD device we use here. Here is the emboss after applying the VIF DIF filtration you just seen. So this should be the payload we should get after decryption. And here is the wireless emboss frame. You can see here is the counter which changes for every frame, and then here you can see you have a completely random bytes, which is a sign of good encryption. And even if this emboss frame is not read out every time, even if we send repeatedly the same payload, this data changes completely randomly, which is a sign of a good encryption. This is the counter for the AS128 CTR. So only this is unencrypted part, but all of which follows is completely encrypted. If I click button, I speed up the actual transmission. There is a little delay because we have the UART connected, so he's waiting for the GUI to connect, the configuration GUI, but because we don't connect, he simply proceeds in the on-wake function and sends again the data. You can see here the counter is 1, 0, 1, 0, 0, 0, and the payload again is completely random. Yeah, so the sign of good encryption. We can, because this would be too easy to get the data from here, from the printout, I'm using RTL433, which is an open source project to receive all wireless and bus data I can see in my vicinity. So now if I click the button, we should see here the actual transmission. After a while, because the device is waiting for the GUI to connect. Okay, and now here you can see we have an ACRIOS ACR manufacturer, device ID, and we can see the frame here. So I will quickly copy it before it moves away. So okay, now I have the payload. I will use it later. So if I get back to here, what I will show you, this with the filtration, you can check it, but basically this is the way it works. You can modify it if you want. I will maybe quickly tell you the important part. This B28 means how many bytes follows in total. Yeah, so if you count from 09 until to 0x61, it should be in total 28 bytes. So if you modify any of these, the number of bytes, you need to modify this number. This 09 means how many entries, how many lines we will have in the VIF DIF filter, and then you have one entry after another, and this number 02 is the length in bytes of one entry. 02 means we will be matching based on 2 bytes. It depends on your knowledge of MBUS, how deep you go, but here is VIF and DIF. But if the most significant bit of this byte is set to 1, there can be multiple, DIF followed or VIF followed by a multiple VIF, and then DIF followed by multiple DIF, which can give you, I think the limitation is up to 10. Yeah, so you can be matching based on quite a long number of bytes, but very often it will be just 2 bytes. So this is how it is set. If you want to see how I got this filter, which can be quite important, I will for a moment put the frame we received here so that I don't lose it. You can, if you go back in the here in the GUI, you can copy the data without the filter, and then I quite like using this Alexander Miller parser to show the VIF DIF's value. So I will maybe leverage what we have here in the comment, because it's the filter, is the frame without the filter. So I will copy the value so that it doesn't take too long. So this is what you would receive on MBUS if there would be no filter applied. If I click parse, you can see here the values, but you don't see VIF DIFs. You need to enable the expert mode. I click on parse, and here you can see different DIF and VIF values. So for example, the fabrication number has a DIF of 04 and VIF of 78, and if I now switch back here, 0278. Yeah, this is how you assemble your filter, by putting here only what's interesting for you. Okay, so here you can see the example how it works, and after the filtration you only see the values you wanted. And now I'm getting to the wireless and bus frame format, the one which I already captured here. Here is you can see byte by byte description of the payload. The first byte is the length, the total length of the frame. Then comes the control field, manufacturer ID, identification, version, etc., etc., until the CI, which is an entry which tells you what is the type of data which follows. A0 means there is an application specific encapsulation, and first 4 bytes of what follows are still unencrypted, and this is the counter value which must change for every transmitted frame. So we have in total 4 billion of frames before it wraps again. But if you take 3 minutes of transmission period and 4 billion of transmissions, it will give you some centuries. Then encrypted, it will look something like that, or completely random. However, decrypted, you should have 2F2F, which is a sign of good decryption, and then there should be the actual MBUS frame, 6, 8, etc. Yes, an MBUS frame starts with 6F, length, and then 6, 8, and then follows the rest, and it ends with 1, 6 at the end in hex. So what we can try, I will apply the approach which is described here, only by looking at the captured frame, and I will use our tools to decrypt it so that you understand how this can be done. Important side note is that it depends on the tool you use, but the payload doesn't look the same if you include the CRC or if you don't include the CRC. Because I have done this experiment before, I know that the RTL433 project, it includes the CRC at the end, so these 2 bytes are CRC. So I will directly delete them right now, like this, and I will only use the frame as is for the decryption. So what we need the encryption key, which is here. Because our device was not provisioned, it has an encryption key of all Fs. Even if we use the internal secret key, if there was no provisioning done, because this is not a production PCB, production device, it is not provisioned, so it uses the key of all F. The second thing you need for a decryption to happen, you need to have the initialization vector. There is, if you check the script, we use the convention that the initialization vector is done in a way that it's the ID of the device repeated twice, and then there is the counter value repeated twice. So this is the initialization vector. In our case, it will not be what you see here. If we check the frame format, the identification is 1, 2, 3, 4 from 5th to 9th byte. So if I check here in what I have received, it goes from 7F to 3C. So this is our wireless MBUS or identification. So I will copy it, and I will open in another tab, which I have already done, but I will show you where the link is. So here I have opened the ACRIOS backend, but I forgot the link is also here to make it easier. So this is the link. It will open the very function of the backend where you can see a tool for AES decryption, but it is a standard AES 128 CTR decryption, so you can use any decryption tool you find. You can use Python, you can use JavaScript. It is implemented in a lot of tools, or you can contact us and we can help you with that. So this is the initialization vector, so I will put there the ID repeated twice. Then if I check the frame, I can see here the counter value. It is quite visible because we are at the beginning. There are a lot of zeros, so you can see there are 0, 0, 0, 0, and if I read from right to left, and then there is 0, 2. So I copy it and I put it here twice, like this. So this is the third frame, because the first frame is all zeros, second frame is 0, 1, 0, 0, and third frame is 0, 2, 0, 0. Then I copy the payload. Where the payload starts? Well, as you could see here, the encrypted payload starts with the 2F2F, so we need to exclude the counter. So right after the counter, we have here 52, and then it continues. I remind you that I removed the 2 bytes at the end, which again it depends on the receiver you use. So I take this, and this is the encrypted payload. I put it here in data hex, and then I click on execute, and voila, I can see 2F2F, which is a sign of good decryption, and here I can see the actual emboss frame, which I can copy in clipboard. And if I check further in the description, you can see here is a parsing. So I open the parsing. You can of course use what's provided by Mr. Miller. I disable the expert mode, and you can see here the thing we read out, and there is also today's date. Yeah, it's matching. It's something like 10 minutes ago. But you can also use our backend, which uses libemboss internally. If I decrypt it, you also have the value and fabrication number, temperature, etc. Yeah, so this is how you read it out. You can see that what we have done in this video, we securely transferred wirelessly emboss data after filtration from an emboss device to a wireless emboss infrastructure, or as I mentioned in the beginning, you can use our NWD variant of our device to receive the data as well. Here is a troubleshooting part. Of course, if the device is still sending empty payload, there can be some problem with the connection of the emboss, or the settings of the baud rate can be incorrect. You can check the troubleshooting here. If you need further support, you can contact us on support@acrios.com, or you can write me at novak@acrios.com, and I'm sure we'll be able to help you. So thank you for watching, and see you next time.